I'm going to be talking about structure-function relationships of polyester coacervates as in their application for hemostats and as drug carriers. So I did talk a little bit about this already in my RP, but a quick overview of coacervates. Coacervation is a form of liquid-liquid phase separation where you start with a homogeneous polymer solution, and through some triggering condition, which is oftentimes a change in pH or salt concentration, in my case, change in temperature. There's also effects of charge neutralization in polyelectrolyte solutions. Through that triggering stimulus, we go from a homogeneous solution to a coacervate solution, which is microphase separated. Over time, this microphase separation can condense, where you end up with a polymer-rich phase, which is the dense phase, and a polymer-poor phase, which is the dilute phase. And so that's what we see in coacervation, and that's how we use these materials. Particularly for thermoresponsive coacervates, we measure them by the cloud point temperature, or the TCP, which is measured by doing a temperature sweep of the material and taking the transmission or absorbance and converting it to the transmission, and the point at 50% transmission, that temperature corresponds to the TCP, and the TCP just helps us determine how handleable our coacervates will be at a particular temperature. The 95 to 5% transmission range also helps us determine how broad that transition will be, which relates to a variety of facts such as molecular weight. And the cloud point temperature is also a function of the polymer composition, where, again, the molecular weight has a big influence on this, but the hydrophobicity, hydrophilicity, so the water lovingness of the polymer also affects the TCP, in addition to the concentration of the polymer in solution and the solvent concentration. So now we'll talk about coacervates as hemostatic materials. To begin, the reason we want to use coacervates is that, first of all, they are a flowable material. They're very inherently liquid-like, especially for our thermoresponsive materials. This is really helpful with their ability to flow and fill wounds and get into crevices that would otherwise be unreachable. And so in this schematic, we're seeing, a wound that has been formed, particularly in soft tissue, which is what this application is for. You can apply the hemostat to fill the wound and over time cross-link and allow blood clotting to create a barrier to blood flow, and ideally a clot, which can save lives, especially in situations, for example, with military trauma, where hospital care is not very accessible, so something to stop blood flow and preserve life is very necessary, especially to preserve patient life before they can reach a hospital. So this is a schematic for the strategy of the compositions of my coacervates. First, we have a thermoresponsive component, and the percentage of this component helps to influence the TCP the greatest, and so that allows us to control what temperature the polymers turn from that homogeneous solution to a coacervated solution. Then we have an aromatic component for adhesion, and we particularly focused on looking at catechol contribution versus phenylalanine contribution, where catechols are known to be very important for muscle adhesion to wet and dynamic surfaces, so we can harness that ability for a hemorrhaging situation, which is again a very wet dynamic surface. But in order to really understand the contribution of these hydroxyl groups compared to a phenylalanine group, which by itself can also form a coacervate, we're incorporating something that does not have those hydroxyl groups to better understand that contribution, and to also see if a catechol is even necessary. The starting material for this monomer is very expensive, so if we could make it from a less expensive material, that makes it more commercially accessible. Lastly, since coacervates, and particularly my coacervates, are extremely liquid-like, they have a high amount of water, it's 50 to 80% usually, we want to be able to cross-link these materials so that we can get long-term cohesion and improve the adhesion, and we can do this in a couple of ways. One is by incorporating another monomer into our backbone, and we've chosen amines because they have been shown to be used very frequently in adhesion, and so we want to, and especially hemostasis, so we want to be able to see whether or not it's having the impact we are hoping for. And also, if we add genopin to the solution of our coacervates, genopin is a known crosslinker for primary amines, which is what lysine is. And so in that way, we can cross-link our polymer to our tissues and improve the cohesion and adhesion of our materials to our tissue surface. So this is the final successful compositions of our polyesters. We have an 80% bismethoxy, or thermoresponsive component, with 20% phenylalanine. The second one is 80% thermoresponsive component, 20% catechol, or dopamine mimic, which is dopamine is the enriched component of muscle proteins. And then the last composition is 70% thermoresponsive component, 20% catechol, and 10% amine. The reason for a reduction in the thermoresponsive component is because the amine is actually more hydrophilic than the thermoresponsive component. So by reducing and balancing that component, we're able to have a handleable TCP and also a good ratio of catechol to be able to better compare these two polymers. So when I performed coacervate rheology, we have a pretty surprising relationship with genopin. Genopin, like I said, is a amine crosslinker that is known to very stably and very easily form these crosslinks. And so if we start by looking at the coacervates by themselves, we see they do behave pretty liquid-like. They have low moduli, and particularly the phenylalanine coacervate tends to be a little bit denser because it's much more hydrophobic. So more of that polymer is going to go into the dense phase as compared to the catechol or lysine-containing polyesters at the same temperature, and so that's why we see a slight improvement in the moduli. These two spots represent blood components by themselves, where we have blood by itself and then blood with genopin, and we see they behave much more solid-like, especially compared to our coacervates. And the interesting thing happens when we combine these materials. And so first, if we look at the phenylalanine coacervate, which doesn't really have any functional groups to cross-link with genopin, we do see that phenylalanine plus blood without genopin has better moduli than with genopin, which is expected. If we look at the lysine coacervate, I apologize, it's a little hard to see, but if you look at the lysine coacervate by itself with blood, you do see, first of all, a significant improvement, and then, of course, the expected additional improvement when you add genopin, which would make sense because we would expect genopin to cross-link those amines. The most surprising result, however, is that with the dopamine-only coacervate, so there's no amines, genopin does show an improvement in moduli. It's a little bit higher behind this lysine plus genopin point. And so the interesting part, right, we wouldn't expect catechol to be able to cross-link with genopin and cross-link with tissue in the same manner as we would with primary amines, but we do see an improvement in modulus anyway, which is great for hemostasis, but a little bit surprising for our chemical understanding of what's going on. When we did some in vitro clotting time tests, initially these results don't look extremely promising, but they do have a similar trend to our in vivo data, which I will be showing next. And we have a few trends that we can see that are still held true, where, first of all, in most of these scenarios, genopin is improving the clotting time, where we would expect that a little bit because genopin should be cross-linking with blood, and the amount of blood in these samples is higher than in the rheology samples, so predominantly that effect will be greater. But it's also a little bit surprising to see that in the lysine, the clotting time is actually worse than any of our materials, which is very different than what we've seen in literature, where materials such as chitosan, which is a polysaccharide that is enriched in amines, that material is used dominantly in the field. And so the fact that amines are actually inhibiting our hemostasis, or at least clotting time, this is an in vitro test, especially compared to phenylalanine or our catechol, is very surprising. Lastly, we tested these mats that were graciously provided by the Mishwani, and we do see that our electrospun mats can clot blood a lot better than our coacervates, and so that, of course, warrants further investigation as to why our coacervates maybe are not performing as well. So next we did, or last I guess, we did in vivo studies on a mouse liver hemorrhage model, where we take a mouse, we give him a laparotomy, we expose the liver and give a controlled incision of approximately 5 millimeters long by approximately 2 millimeters deep using a surgical knife. And in this way we can create a controlled wound to the best of our ability minus human error. We were trained by vets, so this procedure was very highly standardized and performed to the most stringent degree we could achieve. Compared to the control, which is free bleeding, all of our materials are better at inducing hemostasis, and that is a statistically significant finding. And I should also note that even the control free bleeding, all of the mice did survive, so we didn't have any mouse death in any group. But the more interesting thing happens when you start comparing our coacervate materials with cotton gauze, or even with the mats, or in combination with coacervate and mat. So when we look at the contribution, first of all, of genopin, it's kind of inverted compared to our in vitro study, which again is surprising, where we see that at least the averages show that adding genopin seems to make hemostasis slower, but this is not a statistically significant finding, so more research should be done on whether or not genopin is really good at inducing hemostasis in an actual hemorrhagic model. Next, when we compare our coacervates to gauze, we see that phenylalanine without genopin performs similarly, so do our lysine materials, which is good, they should be hemostatic. But really, the dopamine coacervate and our combinations and mat groups, they all perform better than cotton gauze as a statistically significant finding. So this is great because cotton gauze is the go-to material for hemostasis, so if we see that our materials are performing better than what is typically used, that is a promising result. That's very helpful. That's our goal. Next, if we look at specifically our combinations and our mats, there isn't much statistical difference between the dopamine coacervate by itself compared to the combinations, which makes a little bit of sense. If you combine the performance of the mats with the performance of the coacervates, you would expect it to be somewhere in the middle, and therefore, due to the amount of error, you don't see a statistical difference. And finally, when we look at our carboxylic acid mat, statistically, it is not better than any of the other mats, even though the average does show that it should be better. And so this, again, warrants further investigation, potentially on larger animals, so that we can improve the sensitivity of our models and reduce some of that error and better elucidate some of these trends. Finally, if we look at the wounds that are created and their responses to our materials, we see, first of all, in an active bleeding situation, our coacervate is able to displace blood. You can see that this blood was originally on the interface and has been pushed away from the wound by the coacervate. If you look at the mat also does what we hoped it would, where it absorbs some fluid and concentrates blood components at the surface, and it surprisingly did not absorb, the blood components surprisingly did not transfer through the mat, but that's a good thing because we want them to be concentrated on the surface where hemostasis is needed the most. If we look at the final wounds after hemostasis is achieved, or after the 10 minutes of the experiment, we see that our coacervates are able to induce hemostasis, but the wound stays approximately the same size as it did after it was freshly made. So, the depth of the wound allows it to open up a little bit, and so you see kind of a valley shape. And so, ideally, the coacervate would fill that and induce clotting, which in the catechol and lysine-containing polyesters, we do see that, where at the very least we see that the catechol and lysine are oxidizing. That's what this darker color is. Unfortunately, clotted blood also has a similar appearance because that is also oxidizing. So it is a little bit difficult to say for certain whether oxidation or clot formation is the primary mechanism of hemostasis, but both are most likely happening simultaneously. And if you look at the wound, the darker color of the wound does indicate that some type of barrier has been formed, and obviously the coacervate has filled the wound in order to create this barrier. Most interestingly, the electrospun mats actually are able to pull together the sides of the wound. If you compare the coacervate wounds where the wound shape is still more of a valley and the coacervate is able to go in, the mat, through probably its wicking ability of moisture, is slowly pulling the sides of the wound together, and due to the concentration of blood components at the surface, it's able to form an effective clot, and therefore the size of the wound has also decreased after the point of hemostasis. Next, we'd like to look at coacervates as drug carriers. systemic versus localized delivery is a big issue in a lot of drugs. When you have systemic delivery of a drug, that means it can travel across your entire body. Oftentimes, off-target drug interactions introduced through this method can cause a lot of side effects, which is not great. Even, for example, in chemotherapy, when the chemo drug can interact with non-tumorous cells, that can cause cell death and cause horrible side effects, such as, for example, like your hair falling out. So having localized delivery is very important and very desirable, where you can encapsulate a drug in some type of device and thus be able to force the drug to stay in the target location. Coacervates are really good for this because, first of all, they're able to localize delivery. They're able to encapsulate drugs and keep them at the site, at the target site, for long enough to perform their function. They're also flowable, so in spaces that are irregularly shaped or perhaps very small, you can concentrate the drug in the coacervate and thus comfortably for the patient perhaps inject the coacervate into a particular space, such as in the joints or the knee, where there's very little space and it can be very uncomfortable to have, for example, implants put in there. So something that's conformable and can adjust to movement is very desirable. So we chose two different polymer compositions to highlight the effect of pendant groups on encapsulation and release, and we're able to study these interactions through a few different techniques. So the two polyesters that I have used are a 15% phenylalanine group and a 15% tryptophan group, and colchicine was the drug target that we looked at, which colchicine is used for gouty arthritis treatment, and unfortunately, colchicine does have side effects, particularly nausea, vomiting, constipation, diarrhea. These are very common side effects, but obviously the pain relief is perhaps more important than some of these side effects because none of them are particularly fatal. But being able to localize delivery to the site of injury or pain would be very helpful in mitigating these side effects. So if we look at DOSI NMR, which is diffusion ordered spectroscopy, we can look at the changes in interaction strength when the polymer is in a homogeneous solution versus when it's in a coacervate and potentially encapsulating our drug. So at low temperatures, we would see that the polymer is homogeneous in solution. And if we look at the diffusion of colchicine, it's at approximately 0.4. When you add colchicine to the phenylalanine polyester, you don't see much change in the diffusion. It's still pretty close to 0.4, but when you look at it with tryptophan, you see that it is slightly slower. Now, this is not an exact, I have not been able to quantify this due to the spread in peaks, so this is not an exact science necessarily when I'm saying that it's diffusing slower. I can't give you an exact number, but you are able to see this effect pretty clearly, especially when you look at specific lines of diffusion. Now, when we have a higher temperature, first of all, everything will diffuse faster because increasing temperature provides more energy to the solution. But when our thermal-responsive polyesters are at higher temperatures, they start to coacervate and therefore encapsulate any materials around them. And so if you look at, first of all, colchicine by itself, it is diffusing much faster. It's at approximately 0.8. But when you look at it with the phenylalanine coacervate, you can first of all see that the coacervate is probably diffusing almost as slowly as it was at low temperature due to the coacervation behavior. And there's much more of a spread of peaks in the colchicine band. So the phenylalanine polyester is able to interact with the drug. It may not be slowing it down very much, but it is having an effect and causing a more of a distribution of diffusion populations. If you look at colchicine with tryptophan, there's a much clearer effect on the slowing diffusion of colchicine, where if this line is at approximately 0.8 and colchicine and phenylalanine is at approximately 0.8, whereas by itself it's at approximately 0.9, with tryptophan it's at approximately 0.7. So it's certainly diffusing slower compared to by itself with tryptophan, but in the presence of tryptophan, it also appears to be diffusing slower than in the presence of phenylalanine. And so what we can pull from this data is that most likely tryptophan is interacting more strongly with colchicine because it's able to hold on to colchicine better and form these larger complexes that therefore slow the diffusion, but it's not an exact calculation, so it's maybe not the best technique to show this for coacervation. If we look at STD-NMR, which is saturation transfer difference, we see a similar trend and perhaps slightly more quantifiable data that can show a much clearer difference. So if we look at the contribution of saturation transfer to colchicine at low temperatures with phenylalanine, so there's no coacervate, we can see that part of the molecule is receiving more saturation than the other. These two peaks here correspond to colchicine, where this peak at a higher ppm is corresponding to the 7-membered ring aromatic protons, and at the lower ppm it's the 6-membered ring. Now ideally you would see a ratio of 2 to 1 if both protons were receiving the same amount of saturation, but we see a ratio of 2 to more like 0.6, 0.5, which shows that the 6-membered ring is probably receiving less saturation and is therefore most likely further away from the phenylalanine pendant which we've saturated. This shows that when phenylalanine and colchicine are stacking, the phenylalanine ring is most likely stacking on top of the 7-membered ring as opposed to the 6-membered ring. And at high temperatures, we see a similar trend where, again, the 6-membered ring side is receiving lower saturation, but especially because the coacervate has been formed, we do see a difference in saturation transfer overall, where the transferred peak is now, has a much higher signal compared to the colchicine peaks. STD-NMR is very sensitive to the rate of binding and the binding strength. So molecules that bind weakly or moderately up to the saturated material will have relatively high signal compared to materials that bind very strongly or not at all. Since we have this data of low temperature versus high temperature, we can better decide whether or not colchicine is binding to the coacervate strongly or not at all. And since it is clearly binding at low temperatures, we can see that the decrease in saturation transfer is most likely due to stronger binding due to encapsulation. With STD, we see a similar trend. However, it's a little bit more obscure because unfortunately, the saturated peak is no longer the highest intensity peak, which it really should be since it's a difference in transfer. So if you saturate a proton signal, it should disappear, and then if you take the difference from a normal spectrum to the saturated spectrum, that should have the highest intensity. The way that I would explain this is that if you think about the rigidity of a phenylalanine pendant versus a tryptophan pendant is much larger and can potentially behave more like a rudder and behave much more stiffly. So rather than transferring the signal, spin diffusion could occur much faster, and therefore the saturation difference would not be the highest signal for the saturated peak. So because it's not the highest signal, these values are perhaps not excellent quantification, but I was not able to repeat the experiment, so this is what we have to go with. But we do still see a similar trend where the tryptophan is most likely stacking on top of the 7-membered ring side because that is receiving more saturation than the 6-membered ring side. But if you compare these ratios to phenylalanine, we see that the 6-membered ring side is receiving more saturation with tryptophan than it would with phenylalanine. This makes sense because tryptophan is a larger molecule, so if it's spreading out a little bit further, it's simply closer in distance to the 6-membered ring, even if it's still stacking primarily on top of the 7-membered ring. Then again, if we compare low to high temperature, we see a significant change in saturation transfer, where the signal for the colchicine protons are much lower, which we would attribute to, again, an increase in strong binding due to encapsulation. Now, I've been talking a little bit obscurely about these stacking interactions, so here's a schematic, where if you look at colchicine, this is a phenylalanine pendant group stacking on top of a 7-membered ring group. It's pretty far away from a 6-membered proton, or from the 6-membered ring, but if it is still able to provide saturation transfer, then we know that it's still coming into close enough contact to the phenylalanine pendant group. If we compare this to the tryptophan group, we see that simply distance-wise, the tryptophan is able to reach much further across the colchicine molecule, so both sides of the colchicine molecule are not as far away from the tryptophan pendant as it would be in the phenylalanine pendant. Additionally, we can sort of determine the orientation of the tryptophan group based on the saturation transfer of the tryptophan groups. In phenylalanine, all the protons are symmetric, so they should all be part of the same signal. So if you saturate that peak, in theory, there's not enough difference to really be able to give an orientation of whether or not the pendant attached side or the free side is necessarily interacting with the 7-membered ring. But with the tryptophan pendant, the protons on the 5-membered ring side are different than the 6-membered ring side, and so we were able to determine through the interactions and the transfer that tryptophan is most likely stacking with the 6-membered ring side on top of the 7-membered ring side, and thus it's still able to transfer to the 6-membered ring side of colchicine. The DOSI and STD data does align well with our in vitro drug release study. Drug release studies are a very common way of validating methods for seeing how tightly drug devices are able to encapsulate other drugs. And so we do see that the tryptophan is over time releasing slower and releasing less colchicine as compared to the phenylalanine group, even though they both are relatively similar in terms of release profiles. Both of these coacervates we would expect to have diffusion-driven drug release, and so the profiles being similar makes sense. But again, the DOSI and STD data claim that tryptophan is binding stronger to colchicine. Since the release is also slower, our drug release data does support that. Lastly, we wanted to look at how genopin reacts with amine and catechol-containing coacervates, because it behaved differently in our hemorrhage study than we would expect it to as based on literature. So first, if we look at mass spec with a primary amine, butylamine, we do see that genopin does form multiple products in a span of about 24 hours, where we see monomers, dimers, trimers, and even small population of potentially tetramers. And so we did expect genopin to be able to self-polymerize as it's cyclizing with the butylamine. That's a very common proposed reaction mechanism for how genopin is able to react with an amine. If we look at the IR spectra of our polyesters, however, we see a slightly different story. In our coacervates, if we look at the amine-containing polyester, we do see a difference in the before and after of the reaction, and this would not be due to, for example, solvent evaporation. Both of these samples were, both of the before and after spectra were taken from the same sample in a closed vial situation. So solvent evaporation can contribute to decreased intensities, but that is unlikely to be the culprit here. And if we compare our amine-containing polyester to the catechol-only containing polyester, we see that the difference in intensities is much greater in the catechol-containing polyester than the amine-containing polyester. Now, these intensities are normalized so that we can better compare them, and by seeing that the catechol is having a larger difference on these peak intensities, we could assume that catechol is potentially reacting to a greater extent with genopin than our catechol-amine polymers, which again is very surprising because we would expect that, first of all, the amine-containing polymer should interact with genopin very strongly. That's the literature-based understanding. But in fact, when we have both catechol and amine together, the difference is less than with catechol by itself, which would indicate that potentially the amine is interfering with catechol reactions with genopin. Catechol is known to auto-oxidize into a quinone, and that can be a catalyst for catechol polymerization as well. And so that method could be how genopin is interacting with catechol, but if the amine is somehow inhibiting that reaction, that definitely warrants further study. Finally, we did some NMR studies on our coacervating polyesters with genopin, and there's a peak around 4.5 or 4.6 that I attribute to the catechol hydroxyl peaks that has completely disappeared from both spectra. The other important observation about these is that both spectra are almost identical in terms of lack of differences. So the amine peaks, or the amine NH groups, are not disappearing in the amine-containing spectra, and the hydroxyl group peaks corresponding to the catechol are gone in both spectra. So that is again evidence that potentially the autooxidation of the catechol to the quinone is potentially driving this genopin reaction. So in conclusion, our coacervates are hemostatic materials, and we found that catechol only containing coacervates are our best performers. When we look at our drug release study, DOSI and STD are useful tools, especially used in combination, for characterizing coacervate performance, which they have not been commonly used to characterize before. And lastly, genopin is likely reacting with catechol via the autooxidation pathway, but the amine is either inhibiting or not participating in this reaction, which is contrary to our literature understanding. So in terms of future directions, trying coacervates with other components that could recruit red blood cells, such as phosphates or long alkyl chains, would be a worthwhile endeavor for our hemostatic materials. This generation of coacervates was not designed with red blood cell recruitment in mind, because naturally through massive blood loss, coagulopathy can occur, and so relying on the natural mechanism for clotting is maybe not the best way to induce hemostasis and stop blood flow. However, being able to recruit these materials could promote faster hemostasis, and so in the future this would be a worthwhile direction to look at. When we look at our drug carriers, looking at individual monomer effects on colchicine via STD and DOSI would also be a good way of better elucidating some of these interactions. They could also simplify the spectra, so you have less possibility of a distribution of peaks like we saw in DOSI if you use the monomers instead, because naturally that's a simpler spectrum. We can also look at coacervates with other pendant groups, or potentially more or less of a specific pendant group, to see how that affects the drug interaction. We can also potentially look at encapsulation of more hydrophobic drugs, because coacervates are known to encapsulate and concentrate drugs, and so very hydrophobic materials such as aspirin, which is known to be very hydrophobic, but a very commonly used drug. If we are able to concentrate it and potentially release it from a coacervate, that could be very useful. Finally, in terms of looking at genopin's reactivity, if we look at its interactions with catechol via potentially STD, we might be able to better understand where on the catechol genopin is interacting, and that would be confirmation of either the quinone autooxidation or some other effect. Even looking at genopin's interactions with the thermoresponsive component, which we did not focus on since it should not really be reacting under these conditions, that could also have some contribution that we have overlooked, and STD would be another good way of investigating. And with that, I am finished. Thank you for listening very much, and I would be happy to take any questions.
Before we move to the closed door Q&A with the committee, are there any questions from